Okay, so now in a course like this, I think it's only just that we should recall the name of Timoshenko. He was a famous mechanician that worked a lot on analytical approaches, and it's not wrong to say that this course, the content of this course, owes a lot to him. So the title sort of emphasizes three aspects, as I said. One, to sort of honor the name of Timoshenko, and we're going to cover a theory that goes under his name. And as usual, a second goal, essentially a second purpose of this choice of the topic is, as usual, to make a connection to what we covered in ME 231, our first mechanics course. And eventually, in light of the exact results that we derived last time, or we finished deriving last time under cantilevered beam topic, we're going to go back to a very fundamental theory, the beam theory, and we're going to improve that theory. So the fundamental beam theory that we had covered in ME 231 was called the classical or Euler-Bernoulli beam theory. And I will highlight a few shortcomings in view of the exact results that we obtained. And we're going to improve it one step ahead under the name of the Timoshenko beam theory. So for that purpose, let us first recall some results from ME 231. Now, I will remind you of two sets of results. The first one is from ME 231 completely. And by now, I'm realizing that the red color does not show very well on the videos, but I use it anyway. So the first one is statics results. And what I'm going to remind you is internal bending moment and shear forces. And so we're going to work on, again, the cantilevered beam example. And I am going to assume that from now on, because that was our assumption in ME 231, I'm going to assume plane stress. So the beam has height h, length L, and the coordinate system is as we assumed before in our exact solution. Now, what I'm going to do is eventually I will take a cross-section, let us say somewhere here, and I will look at the internal bending moment and the shear force at that point. But before I do that, let me impose some external loading onto this beam. Now, in ME 231, we had different types of loads. The most fundamental in some sense is the distributed load. So I'm going to pick a distributed load, let's say something like this. It could be anything really. And the distributed load, let's say, is like this. This is the default positive direction of the distributed load. I have some favorite letters that I keep using in different contexts. I'm going to call this W. It has appeared before to denote different things, but I hope there is no confusion. So in this case, it indicates load per unit length. Okay? And that is the notation, in fact, that we use also in ME 231. Then what I will do is I will draw a free body diagram. Sort of a free body diagram. So when I take the cut, first I will look at the left part. And also to the right-hand side. Okay? I'm saying sort of a free body diagram because I will keep the support fixed. I'm not going to draw explicitly or indicate the support reactions. I don't need them at this stage. So I have the distributed load. Okay. I have my coordinate system, again, x1, x2. Now, to keep this in equilibrium, of course, we need some internal forces and moments. So our default directions for these, so our argument was in ME 231, let me pick a different color for that eventually. our argument was that I want to pick a convention such that when you look at a cross-section, that cross-section, irrespective of which body you choose, the left or the right free body diagram, when you say, let's say, the internal bending moment is 10 Newton meters, I understand exactly what you're talking about. So this default convention helped us communicate effectively. And this is the internal bending moment default direction, right? Positive. And it is a function of x1, of course, because it's a cross-sectional quantity. This is the default direction for the distributed load. And eventually, we have a internal shear force, the default direction being as such. So we indicated that, as usual, with V. OK, so now, one thing that I would like to remind you at this stage is this is just one type of loading we can have. You will remember I can have end bending moments or forces. I can have localized forces, or at some point I can have a idealized localized bending moment imposed on the structure. In that case, we know that the internal shear force and the bending moment suffer or are subject to certain jump conditions where those localized quantities are imposed, right? So those are just results that we remember from ME 231. We're not going to dwell on that too much. I'm just writing this because eventually I will make use of these quantities, M and V, so I'm just reminding you what they are. So one more thing that I would like to remind you is that for these default directions, we also know that if we take the derivative of m, I'm just putting a prime because it's just a function of x1, derivative of m is equal to v, and the derivative of v is equal to the distributed load. So these are structural results, right? They are from statics. And hence, let's just keep in mind that these are always true. Okay? So there is no approximation whatsoever here. Again, when I integrate, let's say if I'm given W, I can, right? So this expression tells me that if I'm given W, I can use it to integrate towards the V distribution. Once I obtain V, I can integrate towards the M distribution. And integration constants will appear. We know eventually how to solve for them. In fact, I will assign you a homework problem. In fact, I will also solve something in the next time, probably in lecture, to remind you how the process goes. And I remind you once again, if there are any localized shear forces or bending moments in the original loading, then when I integrate, I need to take those into account, as we did in ME 231. So far, so good. That's just statics. So now what I'd like to do is I'd like to move on quickly to deformations. Okay. And really, it turns out that deformations are sort of our worry in all of this. The forces, moments, we capture them. Eventually, it turns out the stresses are almost captured exactly. And in particular, the bending stresses are captured exactly. But the deformations are always problematic because the exact deformation profile eventually depends on the particular assumptions that we will invoke. So I want to talk about deformations. And I want to begin with a simple case, in which case the beam theory, even the one that we learned in ME 231, agrees with the exact results. Okay? And that case is pure bending. Okay, so that's what we are going to talk about, pure bending. So that means eventually I will draw here a diagram. There will be no distributed load. There will be no shear force imposed on the structure, only a bending moment. And the diagram, so the structure is the same. Again, a cantilevered beam. So let's go ahead and draw as before. This is my default positive value for the bending moment. The coordinates, x1, x2, and we recalled the neutral axis last time. It's at x2 equals 0. It's where the bending moment, the normal stress, will be equal to 0. And at some point, eventually, I will take a cross-section that is planar. It's a straight cross-section, and it is perpendicular to the neutral axis as I indicated over there. So this is my plane section that I will keep referring to. Okay? And this is our neutral axis. And I'm going to abbreviate that, just don't want to write it again and again, with NA. Okay? It doesn't mean not available, it means neutral axis. Okay, so pure bending, and hence I underline that, right? It's a very specific scenario. Now, let me remind you that this is not the case that we solved exactly last time. The case that we solved had a vertical force, okay? And when I solved that example, I already highlighted that the solution is actually different from some of the results that we recall from ME231. But in this case, it's different. It's pure bending. And now, this problem, in fact, I encourage you to do so. It's not assigned as a homework problem. It's not the one I solved in class. But it is, in fact, even simpler than the one I solved in class. Take this example. Go through the same procedure. Obtain the stresses. You will see that they are the same. Of course, there is no internal shear force. And therefore, there is no shear stress. But you can eventually calculate the displacements as well. And it will just take you a few pages, 2-3 pages. And eventually, when you go and compare your results with your results from ME231 reference book, you will see that they match exactly. Okay? So nevertheless, when I am referring to what I'm about to state here, I'm going to assume that you can go home and solve this problem based on the approach, the area stress function approach that we developed. And you are able to derive the results that I'm about to express, right? If you like, however, you can assume that I'm referring to all of the results that come from ME231. Okay, so results, I will say here, come from exact solution. Okay, because some of the statements are, let's say, more clear in the context of our elasticity solution, but in ME231, some of the statements are obscured, so they are not as clear as I will state them shortly. Okay, so, but some of the things we can immediately recall from even our 231 class. So under this very special case of loading, when this beam deforms, it's going to deform in a very special manner. So it's positive bending moment. So let's see, let's try to do our best. Okay. Well, I need to shift this down a little bit. I need some space, perhaps. Okay, so let's try one final time. Good. Now, the special thing about this deformation is that under pure bending and loading, this thing deforms in such a way that if I draw a line from the end, okay, and I draw a line from here as well, these lines meet at a center, which we called just generically O in ME231 as well. And I can draw the neutral axis. Okay. So in other words, after under the action of pure bending, the deformation is such that I seem to have a slice from a circle. Okay. So it's a very neat deformation. And to indicate that more explicitly, we're not going to really directly make use of it, but I'm going to say that this is the radius of curvature that we introduced. the radius of curvature is constant. So it's a perfect slice from a circle. So that's rho, okay? And eventually it is a constant and it is greater than 0. In this case, because we are in a case of pure bending. All right, good. So that's what's special about pure bending. Now, there's something more, something also special about pure bending. This is the neutral axis. And initially, I've taken a plane section that is perpendicular to the neutral axis. Under pure bending, both even the classical beam theory or inconsistent with the exact result. So if you go ahead and solve for the exact result, you will see that plane sections remain plane. And after deformation, they remain perpendicular to the neutral axis. Okay? This was our classical assumption from ME 231. We already saw in the last example that if I didn't have a bending moment, but rather a vertical force, this was out of the door, right? It was not satisfied anymore. The plane sections did not even remain plane, so talking about perpendicularness really didn't make so much sense to us at that stage. So, but in this case, everything is as in ME 231, and that's the exact result. All right. So now for that, to sort of talk about what it means for plane sections remaining plane and perpendicular to the neutral axis after deformation, I'm going to introduce a few quantities. First of all, I am going to introduce a new quantity. I'm going to call that V. It's going to be a function of x1 only, and it is simply the displacement in the two direction evaluated at the neutral axis. And I'm going to call this, just so that we immediately understand its meaning, I'm going to call this deflection, as actually we did in ME 231. Okay? So I don't want to carry around U2 x1 evaluated at 0. It's easier to just refer to V. And then when I take derivatives, I can just say V prime, as I will do shortly. So for instance, now I can define the angle that this line makes with the horizontal axis. And the angle is the derivative of V. Okay? So V prime is the tangent of the angle that this red line makes with the vertical axis. And in this case, obviously, beta is less than 0 because the slope is negative, right? But also, we recall that deformations are small, and therefore, tangent beta is approximately equal to beta. And therefore, we have a quantity that is a function of x1. Let me also box that. Okay? These are some fundamental definitions that we are going to refer to. Okay? So the deflection along the neutral axis is a function of V, and therefore the angle beta is also a function of x1. All right. So that's where we are so far. Just to sort of remind you at this stage, it's not really important, but you can also remember that actually the radius of curvature can be calculated by 1 over beta prime. Okay. So now, so far so good. Now I'm going to state a number of things that pertain to the solution. In fact, I'm going to formalize the observations that we make from this exact solution, which I have depicted graphically. So here I'm going to say that for this problem, we find or observe. Now, observe in the sense that I have already stated the observations, but if you like, you can use find, which means from the exact solution. So in any case, we can write the two following items. The first one is plane sections after deformation, they remain planar. planar versus a line that sort of wiggles, right? Because it deforms. It doesn't need to, after deformation, remain as a line. It could have been some curved line. That's not the case in this scenario. So plane sections remain plane. Okay. And the second one is that plane sections which were initially perpendicular to the neutral axis remain perpendicular to neutral axis. Okay, so those are the observations, or those are our, yeah, right. Those are our observations, and in a mathematical context, we would find, or we can translate these observations into the following mathematical statements. So there are two sets of statements that go along with plane sections remaining plane. The first one is the only way a plane section can remain plane is that U1 is described by a rotation. Okay? And we've talked about rotation many times. By this time, we know that if theta is of course, constrained to be a small rotation of x1, because it's a cross-sectional property or a quantity. Okay, and the positive direction according to our coordinate system is clockwise, and therefore we have a minus sign. Okay, so because if theta is positive, x2 is positive, we expect u1 to be negative, right? So that's based on our knowledge of what rotation means. That's the only way plane sections can remain plane. So moreover, if plane section, so what is theta? I don't know yet. It is some small angle of rotation, okay? But I don't know what theta is yet. I just know that because plane sections need to remain plane, I need to be able to express u1 as a linear function of x2, the constant having to do with rotation. Now, the second observation I can make is that theta is a function of x1 only, and theta prime must be equal to m over ei. Now, these two observations, both of them go together. Whenever plane sections remain plane, these are the two conclusions I can make. Now, why is the second one true? Perhaps by this time this one is obvious. Now, the second part may not be obvious at first sight, but if I first write minus mx2 over I, we know that that's equal to sigma 1, 1. This is a result that we derived last time. This is a exact result, right? But it also holds for all the approximate theories, including the classical beam theory that I will remind you, and then also for the Timoshenko beam theory, which is one step ahead of that classical version. Okay? So this is always true. In fact, it was also true for the case that we solved with a vertical force. So this is something that always holds. Okay? But now, what does not hold always is, now first of all, I'm assuming plane strain because epsilon 2, 2, 3, 3, etc. are 0. Sigma 1, 1 is always equal to E epsilon 1, 1 for plane strain. Now, the critical part is to say that epsilon 1, 1, it's U1, comma 1. And that is equal to minus theta prime. I'm sort of squeezing everything here, but I hope it's clear. Minus theta prime x2, right? So these two equalities always true, but epsilon 1, 1 is defined by u1, comma 1, always true. And u1, comma 1 under this specific observation is comma 1. This is not a function of 1. So minus theta prime x2. And so now if I look at these equalities, the minuses cancel, the x2s cancel. So if I move E over here, I find that theta prime is equal to m over EI. That's my conclusion. Okay? So that last step pertains to plane sections remaining plane. Now, then we also have an observation that pertains to, or observation that is induced by plane sections remaining perpendicular to the neutral axis after deformation. Okay? And that observation is concerning this angle. This angle, so far I don't know what it is. Okay? But suppose I know the deflection, so I can calculate this angle beta. Okay? So plane sections remaining perpendicular to the neutral axis eventually invokes the conclusion that this unknown angle theta is exactly equal to beta. Okay? So theta is not an unknown. If I know the deflection, I can take its derivative, obtain beta, and that's what really theta is. Okay? Or let me write it in a slightly different way. V prime is equal to theta. So looking in the other way, if I know what theta is, right? If I can somehow determine what theta is, then I know V prime is equal to theta. I can integrate this quantity towards the deflection, right? So what we need to do is, this assumption we need to watch closely. Because it's the critical concept that will form the basis of Timoshenko beam theory. Okay? So again, both of these you can either find or observe from your ME 231 results. You can open your book, or you can go ahead, do the derivation, and you will find exactly that U1 is equal to minus theta x2. And if you take the derivative of the deflection, you will find that it is equal to the same constant, which we call theta. Okay? So go ahead and really do that derivation yourself, just to sort of feel more confident in these statements. All right. Any questions so far? Okay. Now, those are nice results. So far, whether you do the exact solution or you proceed with any beam theory, everything will agree with each other, exact or approximate beam theory. In fact, beam theory is not approximate anymore. The solutions will overlap. Okay? But now, suppose we introduce a shear force, and we can do that in multiple ways. I can put a shear force, vertical force here at the end, or I can put a distributed load, or I can put a shear force, a vertical force, anywhere along the axis of the beam. And whenever we have a shear force, this picture is destroyed. Okay? So in other words, this solution that is exact for these statements which hold for pure bending will not hold anymore. And let us see why. Now, I'd like to emphasize again and again that this shear force is the culprit. It's responsible eventually for all the trouble. Okay? And I'd like to emphasize why it causes a trouble. So it causes eventually two troubles. The first one is, let's look at a very simple shear deformation. And that very simple shear deformation is I take a square. Okay? If you like, you can think of this as being in the presence of some vertical loading, a infinitesimal element somewhere on this beam. Okay? But if you like, it's just a square of finite size. I will draw two lines that are initially perpendicular to each other. Okay? And I am going to impose a shear force. So I'm in 2D. So this is the positive sigma 1, 2. And I know that after deformation, the square is not going to be a square anymore. It's going to look like this. And what concerns me at this stage is, due to the presence of this shear force, these lines now will not be perpendicular to each other anymore. In fact, that is precisely the definition of the shear strain that we had used in ME 231. So this is 2 epsilon 1, 2. So shear strain is not 0. And when it's not 0 because there is a shear stress. The lines that are initially perpendicular to each other remain as straight lines, but they are not perpendicular to each other anymore. So the presence of sigma 1, 2, which has to do with internal transverse shear force, right? So whenever I have V, I will have a sigma 1, 2 distribution, prevents perpendicular planes, right? Hence, so let's think of some idealized world where plane sections did remain planar straight as they do here. They are, by some influence, constrained to do so. We would observe a violation of the assumption that they remain perpendicular to neutral axis after deformation. So what I mean is the following. This is the example that I have drawn at the beginning of the lecture. This is our example loading, right? So after deformation, this thing is going to bad. So now what I'd like you to do is compare this qualitative picture. It's certainly not precise, but qualitatively you can compare it with the deformed configuration that I have drawn over there. So I'm going to try and exaggerate, of course, highly exaggerate, in fact. And I am going to exaggerate by first, well, already by the deformation it's exaggerated, but I'm going to draw the neutral axis at x2 equals 0. And now I'm going to draw this line. Now you already see that perhaps this line is not perpendicular to the red line on purpose. And I'm going to exaggerate the other line on purpose here. Perhaps here it's better. Okay. So for sure, not quantitatively correct, but this is alpha is not equal to pi over 2 is the message here. Okay? So it is not anymore perpendicular. So shear stress, we know, will, even if the lines remain perpendicular, it will prevent them from being perpendicular after deformation. So now I'm thinking about some magical world where in this scenario, right? So I should put an exclamation mark. It is a magical world. In this type of a loading, plane sections would not remain plane. But suppose they were somehow constrained to remain plane. So even if they did remain plane, after deformation, I know that due to the presence of shear stresses, the lines cannot possibly remain perpendicular to each other. So that is the first, let me say, influence of the presence of shear stresses or shear forces. So when I look at these two observations, this one is immediately going to junk, right? So now I can think about also the first one. And we know from our solution that we worked on last two lectures that from our solution 2, and instead of wording that, I will just draw the problem that we solved. From our solution to this problem, plane sections do not remain plane. And in that case, we had observed that because we saw that the U1, for it to remain perpendicular to, well, or for it to remain plane, it has to have a linear dependence on the vertical coordinate x2. And eventually, in our solution, we had observed a cubic dependence on x2, which means that if this is the original line, I'll draw it again with a blue. After deformation, really, it's going to look something like this. That's because plane sections do not remain plane. Okay? So the presence of shear force destroys this picture completely. Right? So that is the message that we get from all of this discussion. Okay. Do you have questions so far? So what I'm really doing is I'm combining 231 observations now. We're trying to go ahead. We are observing that there are some inconsistencies. And now what we're going to try to do is we're going to improve the inconsistencies that we observe eventually in classical beam theory. But I'd like to, of course, remind you what that theory was to begin with. So now I'm going to state, again, a statement that I had verbally expressed last time. So suppose the bending moment, all the effects, and in particular I'm talking about the effects on deflection or deformation. I am assuming, or I'm going to assume, hope that the bending moment effects dominate shear effects. That's what I mean by M effects and V effects on deflection, let's say, effects on deflection. And again, this is a statement at this stage perhaps looks vague. You will remember from ME 231. I have stated it last time, but we will see it more clearly towards the end of this lecture or this topic. So last time we had derived the deflection. I had decompose it into two parts. And I told you that the tip deflection for the cantilevered beam with a tip force can be decomposed into two parts, a normal and a shear part. We didn't immediately see the interpretation of why the first one was normal, the other one was shear. But I told you that the second part diminishes and rapidly goes to zero as H over L ratio decreases. Okay? And it turns out that the second part that diminishes with this constraint, with this condition, is due to the shear force. So under that case, the bending moment effects dominate V effects. In other words, you can say that delta is approximately equal to delta N. Again, we're going to see that more clearly shortly. And this is the condition that is referred to classically as a slender beam. So it's thin and long. Okay? That's what slender beam means. So for a slender beam, therefore, we can expect, and I will reinforce those expectations again and again, we can expect a prediction of V of x1, okay, the deflection of the neutral axis, through this solution diagram. Okay? I always like to draw or somehow pictorize our approach through some sort of a diagram that summarizes all the ideas. And the ideas here are twofold. On the one hand, we have results from statics. And we know that, for instance, if I have the distributed load on the beam, then I know that V prime is equal to W. That's just a structural result. And I can therefore integrate towards the internal shear force distribution. And I also know that M prime is equal to V, and therefore I can integrate that now towards the bending moment distribution. This part is always true. We're not really worrying about this part. Okay? Okay, so that is from statics. Now comes the second part. The second part is now going to propose that, well, I made two important observations, and those two important observations are true in the case of pure bending. And now I'm going to invoke that they also hold, even in the presence of shear force, as long as M dominates V effects. Okay? So what I'm going to say again is that all of those expressions, the blue ones as well as the red ones, still hold. it's a good assumption if I have a slender beam. So let me carry them over here and put them in a diagram. What I am saying is that m over EI is equal to, or let's say theta prime, sorry, here, theta prime is equal to m over EI, right? And therefore, I can integrate that towards theta, and I know that also V prime is equal to theta. And this is our result from elasticity. Right. It's easy to get lost. It's a repetition of what you already know and what we have learned, rephrasing, etc. But I'm trying to do it as carefully as possible, and that's why I've split this diagram into two parts presently, a part that always holds, and a part that is exact if I have pure bending, and it is a very good assumption if I have a slender beam. Okay? So you see the idea here. Suppose I am given a situation where I have some distributed load. I can find V. I can find M. I can take that M, plug it in here. I know theta prime. I integrate towards theta. And once I know theta, I can integrate towards the deflection. I want to find the deflection. For deformation analysis, for beams, that is my primary quantity of interest. Okay? I'd like to see how this structure that is composed of many, many beams eventually deforms. All right. And let me also highlight that beam, it's not only a civil engineering structure. You can see beams on microstructures that have to do with advanced materials. You can see beams in mechanical engineering structures, aerospace, or automotive structures, etc. So it's really a very, very fundamental structural element. That's why we are giving so much importance to this type of a analysis. Okay. So now, if you invoke this picture, which is a very good assumption for slender beams, then you end up with a beam theory that is called the Euler-Bernoulli beam theory, which is exactly what we have covered in our first mechanics course. So that's the Euler-Bernoulli or classical beam theory. Okay, so again, ME 231, right? And I will have to once in a while write Euler-Bernoulli, and I want to avoid that by just abbreviating it as EB. Okay. Okay. So if you're working with the Euler-Bernoulli beam theory, you are already assuming that these together, in a seamless fashion are connected to each other. And therefore, I can write an overall solution diagram that takes us directly from the distributed load to the final quantity of interest, V. So if you want to go from W to V, right? So I'm going to phrase things now a tiny bit different. Okay. Okay, so just lay down your pencils for a second. Let's do this carefully once. So I am given W, the load. Okay. I may not be given W. If W is 0, then I can start from V. If V is 0, then I can start from M. We've done this before in ME 231. So, but let us assume with the most general case where there is a W. So I am given W, and I want to go towards V. But in the middle appears this quantity theta. So I like to rephrase everything in terms of theta. So I like to think that somehow given W, I work with this quantity theta that represents rotation. And from rotation, I make a transition eventually to deflection. So I'd like to start with theta. But the starting point is originally W. But now if you look, you see there is an M here. If I take one derivative of M, I go to V. Another derivative, I go to W, which means if I take two derivatives of theta, I can make a connection to W. And if, indeed, the third derivative, two more derivatives, is equal to W over EI. Okay, so given W, all right, then I can integrate once towards theta double prime. And now that is equal to V over EI. Okay? Then I can integrate once more towards theta prime. That is equal to M over EI. Then I can integrate once more towards theta. Okay? And then I can integrate towards the deflection, which is my quantity of interest. And I can do that because I know that theta is equal to V prime. Okay? So that is the overall solution diagram. You give me W, I can immediately calculate third derivative of theta, go through integration all the way towards rotation, and finally invoke this critical piece of information and obtain deflection. Okay? It's a slightly different way to put things than ME 231, but you will see why I'm doing this. Because eventually, in all of this picture, when I want to improve the shortcomings of Euler-Bernoulli theory and towards making it more, let me say, consistent with the exact results, the only thing I will change in all of this picture is this part. Okay? The red equation will change, and everything else will remain constant. Okay? So go ahead and write that part, and then we can continue. Okay, so now we are going to try to take a step further. Further meaning I'm going to try to go beyond the limitations of this basic beam theory, the classical beam theory. It makes the assumption that this is satisfied. Suppose it is not satisfied, right? So let's say EB theory its prediction quality diminishes as H over L increases. So we ask ourselves whether we can come up or whether we can formulate a better theory, right? So better is something that eventually we will judge. Okay, better in which sense we will see. And eventually the answer is yes, of course we can. And we want to do this, however, in as simple a way as possible. And the approach we are going to follow is called the Timoshenko beam theory. And again, once in a while, I will have to write Timoshenko. Just to avoid that, I will abbreviate it as TI. Now, the Timoshenko beam theory. Let us state two major observations that pertain to it. They are really quite simple, actually. Okay, so the presence of the shear stress is the problem. Okay, first of all, plane sections do not even remain plane. But let us forget this complication. There is a much simpler complication that we can sort of picture in our minds, and that plane sections that are initially perpendicular to each other due to the presence of shear stresses, do not remain perpendicular to each other anymore after deformation. So now let us go back to this diagram. And in this diagram, I have the blue route and the red equation. So the blue route, starting here, already invokes the assumption that plane sections remain plane. Why? Because to take this and carry it over there, I used this equation through this direction. Okay? And this equation says plane sections remain plane. Okay? Let me do my favorite move and remind you. Right? Plane sections remain plane. Okay. So I'm going to keep that assumption. As soon as I invoke that, I can follow this blue route. But I'm going to drop the assumption that plane sections, which are initially perpendicular to each other, remain perpendicular to each other. I know that in the presence of shear stresses, that is certainly going to be a realistic expectation. And therefore, I'm going to allow it. And in this way, I'm going to take a step beyond the earlier Bernoulli beam theory. And therefore, it means that includes or necessitates that I do not make this assumption. I have to assume something else. I don't know yet what so far, but I will make that assumption. So let me state those or write those statements. So I will still assume that plane sections remain plane. And therefore, U1 must still be described through a rotation where theta is a small angle, and theta prime must be related to the bending moment through this equation still. Okay? But we are going to allow the section not to be perpendicular to the neutral axis after deformation. Okay? That's the critical assumption that we are dropping. Right. So once we drop that assumption, we are sort of doomed because our updated solution diagram becomes the following. So I told you that the blue route that we have developed still holds because of retaining the first assumption. So theta triple prime will take us through the relation theta triple prime equals W over EI to theta double prime, which is V over EI, to theta prime, which is M over EI, to theta, right? So far, so good. Theta is the quantity that describes rotation, okay? And given W, I can integrate towards that quantity. But now, the question is, how do I find the deflection from it? Because theta is not anymore equal to V prime, okay? So before we had said theta is equal to beta, it was V prime. And let me remind you, V was U2 evaluated on the neutral axis, x2 equals 0. So that is the missing piece of information that now we need to develop, okay? And once we can do that, then we have a better theory. So let me motivate that update. It is a rather straightforward update, actually. Or let me say, rather intuitive update. And let me motivate it. And too motivated, let's do or make some observations. And again, I would like you to lay down your pencils as soon as you write that much, and let's go through this together. Okay. All right. So elasticity, knowledge of elasticity theory eventually will guide us through, and it's going to do that in a very simple manner. First, I'm going to write the shear stress. I'm going to write the shear stress at any point along the beam. I'm going to multiply it by 2 just for convenience. So the shear stress, it is at any point along the beam, and I'm talking about, at this stage, any arbitrary loading, and I'm talking about the exact result. So it's a function of x1 and x2. It's not necessarily a constant along any coordinate. It can change all over the place. And I have its definition, which is u2, 1 plus u1, 2. That is the definition that we know from ME 230, or sorry, from this course. Now, I am already invoking, in the context of this so-called Timoshenko beam theory, let's see where it leads us, but I'm already invoking plane sections remain plane. So I have that statement, u1 equals minus theta x2. And therefore, this is still equal to minus theta. Okay. Therefore, you can immediately see, by the way, that before we had neglected shear deformation, right? We are neglecting the influence of shear deformation on deflection in the context of the classical beam theory, the one that is not supposed to work if the beam is not really slender. So neglecting shear means immediately from this equation, this is approximately equal to 0. If you like, this is one interpretation. Epsilon 1, 2 is approximately equal to 0. And if this is equal to 0, the only way, or what we immediately have, is an expression for theta. Theta is equal to this quantity, which is beta. That was the observation that is correct for Buer bending, and that was the assumption that we invoked in the classical beam theory. Okay? And here we clearly see that that assumption really does indeed rest on neglecting shear. Okay, but now I don't want to neglect shear. I want to somehow take that into account, right? So what I will do is I will first evaluate this quantity on the neutral axis. And when I evaluate u2, 1 on the neutral axis, it's by definition what we defined as v prime, and that's equal to beta. And so beta minus theta is equal to 2 times the shear strain. So now let us imagine, okay? So if I highlight that, if epsilon 1, 2 is a constant, along x2, okay? So if epsilon 1, 2 is a constant along the x2 coordinate, its value at x2 equals 0 is the same as its value anywhere for all x2. All right? So then, right, let me also, so if this holds, in general it will not hold, right? But suppose it does hold, then epsilon 1, 2 is equal to a function of x1 only, and it is equal to, right, if it's a constant, simply 1 over 2 beta minus theta. It's just we're making a sort of a thought experiment. So in that case, sigma 1, 2 is equal to 2 mu epsilon 1, 2. And so 2 mu times that is simply mu times beta minus theta. Okay? So the only assumption I made so far is that. And therefore, I can calculate the shear stress. I had written the expression last time, so I have to have a minus sign due to our conventions. So this is, of course, exact. Integration of the shear stress over the cross-sectional area with a minus sign is equal to the transverse shear force. And because I am assuming that the shear strain is a constant along x2, then this is simply minus sigma 1, 2 times the area. So from these, I obtain that sigma 1, 2 is equal to minus V over A. Okay. And now sigma 1, 2 is minus V over A. And therefore, what I can do is I can put minus V over A to the right and theta to the left-hand side and write theta is equal to beta plus V over mu A. Okay. Beta, I remind you, it's V prime, right? So our missing update seems to be, right, V prime is equal to theta minus V over mu A, right? Once you give me what W is, right, I can integrate towards V, right? But I had this last missing link sort of not stated. I don't know what it is because I'm dropping the assumption that plane sections remain perpendicular to the neutral axis. So I can so far integrate towards theta, but now with that last piece of information that we have derived, now I can do the integration towards deflection. And I am doing that in a way that now also accounts for the presence of shear stresses or shear forces. So I have now a different theory. Okay? So perhaps this is a better theory, right? So why don't you write so much? And then let me continue a little bit more. Okay. So where do we stand in all this sort of repeated summaries? But I think it's worth it. So where do we stand? Well, so let's think about what we have captured correctly and what we have not captured correctly. One, I cannot be obtaining some perfect theory with this update. Why? Because I am still assuming plane sections remain plane. All right. So I have one shortcoming. It's in my pocket because I know that plane sections do not remain plane, as I know from the last solution that we developed last time. All right. So, but let's forget about that. Now, if we have plane sections remaining plane or not, however, the normal stresses are still equal to minus mx2 over I. So why is that? Because all of the assumptions that I have used never violate that statement. So normal stresses are always captured exactly. So that's good. I am doing something very well. But now, how about the shear stresses? Am I capturing that correctly? No, because I made a very ideal statement that the shear strain and therefore the shear stress is constant along the cross section. Okay, so that's the second layer of approximation on top of plane sections remaining plane. So I am violating two things now, and therefore, even with this update, yes, I do expect, I hope, some improvement over the Euler-Bernoulli beam theory, but this eventually Timoshenko beam theory still will not give an excellent prediction. Okay, so I do not, let's say, so or this may not be a very good update because sigma 1, 2 is not a constant. And in fact, I have developed last time, together, we have developed that the shear stress distribution at any point is equal to minus V, it's a function of x1, Q, the area moment, it's a function of x2 over IT. Okay, so this is exact, right? But we are violating that. So even if plane sections were approximately planar, the shear stress is for sure varying irrespective of how slender the beam is. It's varying in some, let's say, parabolic fashion or nonlinear fashion because of the presence of that Q over there. So this if-then statement introduces an error. So I don't want to sacrifice from plane sections remaining plane, but I want to somehow account for the fact that I messed up here. It's not really a constant. It should have been varying. But I don't want to incorporate a lot more complicated approach into those statements. I want to sort of preserve it, and I want to somehow account for this inconsistency in a very simple way and hope that it works. So to account for this inconsistency, so inconsistency referring to the fact that we have assumed the shear stress to be a constant, but it's not. I'm going to hope, right? And at this stage, it's just a hope. Eventually, it needs to be verified. Hope that if we introduce a shear correction factor, I'll call it K. Everything will work out for the better, and I'm going to do that as follows. I'm going to take this blue equation, V prime is equal to theta minus V over mu A, and I'm going to throw in a factor, K. And now this will be our equation that relates rotation to the derivative of the deflection. And the concept was, the final step we took is the shear correction factor K. Now, what is K? We have to choose K. I don't know what K is yet. Okay? So it is to be chosen. Okay. But apart from that, everything is settled. Right? So next time when we start, I will review everything, where we stand, the exact and the two approximate theories that we have talked about this lecture. I will talk about the exact solution, remind you its features, and then I will talk about the Euler-Bernoulli beam theory, remind you what the shortcomings are, and then I will remind you of this final update and the meaning of the shear correction factor, and then we'll update our solution diagram, and then we're going to proceed with some examples. Okay? So that's all for today. All right, I'll see you next time.